Hello, beautiful minds and curious souls. Welcome back to the Curiosity Dude, the space where we embark on thrilling journeys through the cosmos. I'm Slava, and today, we're diving deep into the heart of our existence, the incredible story of cosmos. Today, we are going to discuss biggest mysteries of the cosmos. Spheroidal galaxies produce incredibly challenging questions regarding our modeling of the cosmos development process. Our problem is heightened because elliptical galaxies grew far away and long ago. As a result, the data that can reveal their arrangement is obscure. Nevertheless, there are mild relations between measured characteristics of the hidden aspects. One such relationship is the central plane of elliptical galaxies. This plane combines three measured amounts: the size, the expanse, and velocities of the stars and the mass of all the stars in the galaxy. A plot of those three measures in three dimensions reveals that they rest on a two-dimensional plane, indicating they are connected. Furthermore, how this came about is a puzzle. What is certain is that elliptical galaxies as observed today are very gently growing and evolving systems. Any association in their characteristics must have been marked at birth. Galaxies now are very gradually developing systems. These mounting relations must have been marked long ago, when the galaxies constituted the associations, providing observational restrictions on how the stellar mass was compiled. We would sincerely like to differentiate our snapshots of the past inferred from the scaling relations with development models. However, unlike disk galaxies, we have no underlying hypothesis of spheroidal galaxy uncertainty in star configuration. Instead, there are phenomenological ideas that propose the notion that consolidations control the gas reservoir. For creating stars, consolidations without gas are called dry consolidations. A consolidation with gas is wet. A wet consolidation involves star development and leads to multiple alterations in morphology. Modeling consolidations tells us that dry or dryish significant consolidations indeed performed a vital role at a redshift of 1 or 2 in valuing for the morphological properties of huge ellipticals. One must also face gas-rich minor consolidations as the feeding source. To break down the massive elliptical galaxies, unique objects, a minor merger means one in which the mass proportion is less than approximately 1 to 10. This needs to be one of the central routes for stimulating spheroid configuration. Mergers of gas-rich foundations supply the gas that settles the stars. Most importantly, the frenzy of the merger compresses and reveals the gas. As a result, the vapor falls into the interior region of the forming galaxy. Once sufficient mass and gas builds up, star formation originates in earnest. The creation timescale can be examined by analyzing the chemical characteristics of the stars. Elements like magnesium and oxygen are generated by massive star supernovae. These stars only endure during the initial 100 million years of a galaxy's existence if there is no additional substantial gas injection. Thus, the magnesium in stars was amalgamated early in the galaxy's existence. However, components, such as iron, are also produced in supernovae, but regularly in supernovae whose ancestors are long-lived, low-mass stars. Numerous billions of years are thus needed to collect the mentioned iron in stars. Thus, the observed iron was manufactured late in the galaxy's development. The proportion of magnesium to iron in distant stars is an adequate archaeological timekeeper. It shows us how much time passed when these stars were being collected. The observed proportion in the Sun dictates the Sun to have produced about 4.6 billion years ago. A high ratio indicates that the stars accumulated over a much smaller time scale. In this way, we discover that vast elliptical galaxies must have developed within 100 million years. These galaxies, by contradiction, formed over numerous billion years. It so occurs that the breakdown time of a massive galaxy was about 100 million years. From this information, we gather those vast elliptical galaxies formed most of their stars monolithically through the primary collapse. Of course, the gas needs to have expanded for a while before reaching the stars. The intensification and the magnesium to iron proportion leave us with an astonishing conclusion. We had earlier thought that the larger the galaxy, the later it appeared, which is undoubtedly correct for dark halos. A result is that the later an object consolidates out of the expanding cosmos, the fibula the average density, and the longer its initial breakdown time, that is the shortened theory. But, in fact, we view the reverse. The data notifies us that the gas element forms stars much more swiftly on a time scale. On the order of the dynamical time range of a massive galaxy, not much star development could have occurred. When the gas was being constructed from many smaller objects, which hindered the gas from producing stars early before, the heavy galaxy was in position. The event between star development time, gathered from the chemical data, and collapse time inferred from size and mass is adequately compelling to support monolithic collapse. Nevertheless, this poses the vital question of why monolithic collapse. We can argue that the beast in the center, the supermassive black hole in the heart of the galaxy, makes a distinction. Supermassive black holes are found at the cores of galactic spheroids, which are perceived as the energetic nuclei of galaxies. They accrete gas from their surroundings and are usually the reservoir of enormous outflows. If lesser mergers and accumulation collect the gas, some new component is required as a resolution. Thus, supermassive black holes could produce the missing link required to conjecture the mystery of elliptical galaxy configuration. The final determinant of whether a galaxy harbors a massive spheroid may rightly be the purpose of the galaxy's central working nucleus. The data for such a missing link originates from a discovery originally made by astronomer Dalton Morgan when he found a connection linking the supermassive black hole mass and the mass of the spheroid. The relationship only makes sense if both develop together at the same time. In the early cosmos, detailed measurements of a spheroid velocity, dispersions, and black hole masses have presented articulate testimony to an informal relationship between active galactic nuclei and spheroid generation. We have noticed that star generation and disk galaxies are ineffective processes. Observe how useless it is. The specific timescale for star configuration, for example, is various gigayears for a galaxy such as the Milky Way. This is an order of magnitude larger than the orbital time, equivalent to the changing time scale. This slowing down of the evolutionary timekeeper results from what we call feedback from continuous star configuration. The feedback works on the gas that has still to form stars. Feedback works as follows. Stars form in a variety of sizes. The more extensive the star, the faster it develops. Stars of higher than about 10 solar masses decline spectacularly inside barely a few million years. Massive stars consume energy prodigiously and quickly exhaust their nuclear fuel stocks. The inevitable conclusion is that the core fails, releasing so much power so fast that the remainder of the star blasts. Radioactive wreckage is expelled that decays into solid products such as iron, carbon, and oxygen. The heart wreckage is cleared up into an expanding shell that ultimately is stopped by the ambient interstellar force. The deceleration of the dense case by the thin interstellar gas is an unstable interplay clause of dense. Cold gas infiltrate the light-warm gas. The shell cracks up and scatters the enhanced debris from the bang emerges into the interstellar medium. The interstellar clouds are enhanced. The processing of gas towards stars is reduced because the supernova rack also includes energy into the clouds. The cloud gas is stimulated. This is not the sole source of feedback. The revolution of the galaxy also mixes up the cloud movements. The galaxy rotates at a uniform velocity when a cloud systematically wanders into an interior orbit. Its speed increases related to neighboring clouds because angular momentum is conserved. A rock on the end of a spinning line has a more meaningful speed when the line is reduced. These shearing changes also stimulate the clouds. The power source is the overall rotational energy of the galaxy. All of this is feedback. There is still feedback from developing stars' magnetic lines of force wire. The interstellar vapor clouds twist and turn up the fields as they close, and, eventually, the field boundaries snap. Magnetic energy is discharged into the vapor assembly of gas, is reduced. Star configuration is delayed. A molecular cloud is extended up to an order of magnitude longer than the free fall time. The discovered gas means violent actions must manage the gas pressure. Cloud internal movements are perceived to be deeply supersonic. The fierce pressure counterbalances gravity since the disturbance is primarily motivated by stellar feedback. Cloud star development rates are self-regulating. global self-regulation is dominated by the star formation time range and by the gas stocks. Star formation consumes the gas stocks. Dynamical intercommunications between stars and molecular clouds warm the young stellar disk. Sustenance of global disk vulnerability need a hard disk in the gas stores to sustain. This is implemented via gas accretion, which becomes about by constant fall from the halo and minor mergers all these active communications, and, therefore, the gas disorder, the turbulence, is shown in the cloud. Interior velocity structures, the supersonic disorder, is thought to represent an essential role in accounting for the survival of star creation and disks. However, the global driving of the disorder, which usually would disappear on a small timescale, is not entirely realized. Numerical simulations of whole disks did not solve unique star formation, and stellar blast simulations have a problem. Following the turbulence's dissipation, the difficulty we have been considering concerning these galaxies presents an insight into how feedback in the universe works. There are some manageable analytic reflections. First, the low performance of disk star configuration lends itself to an outspoken interpretation of the gas section transformed into stars per disk revolution time. We have previously noted that this is recognized globally to be approximately 2%. Second, the section of original supernova energy free for stirring up the interstellar gas, after enabling for radioactive losses, is the proportion of the observed interstellar gas cloud speed diffusion to the velocity at which an expanding supernova relic has the impact of a snowplow and driving all before it. A relic expands initially at 20,000 kilometers per second while it slows down by clearing up ambient gas to nearly 400 kilometers per second. It efficiently transfers its momentum. The proportion of cloud motions to the velocity at which momentum is first adequately maintained happens to correspond with the recognized inefficiency of the gas exchange. This is not a shock. It is assumed that if supernovae indeed manage intense cloud velocities, supernova-driven droplets of hot gas that sweep of cool gas into a compact shell presents us with a self-regulation basis for disk star configuration. The self-regulation is dominated by the interplay between the cold gas storage required for star formation and the contrary feedback connected with extensive stars, including their birth and destruction. One difficulty is that the disk is not a restricted environment. Supernova outbursts trigger the venting of disk gas into the halo. The gas cannot emerge from extensive disks. This is true for disks comparable in size to the Milky Way galaxy. The venting issues in galactic fountains. These galactic streams eventually cool and contribute to the store of cold gas that saves disk variability as a disk galaxy. The Milky Way galaxy is one of the best studied parts of star configuration history. There is a specific forecast for the content of the cosmos from the synthesis of the light elements in the first 3 minutes of the Big Bang. We estimate the mass in interstellar gas and stars. Where are the baryons today? One opportunity is that the halo comprises compressed massive baryonic halo objects called machos, for which there is at best limited evidence. Another chance is that most of the lost baryons are in the form of diffuse million-degree Kelvin gas. The remarkable dark matter hypothesis of structure configuration asserts that there is remaining addition of coal gas. The details of how the gas warms up on communicating with a halo are currently debated. However, the current gas content is expected to have increased the total baryon content over the past 10 billion years, indicating that a typical galaxy should contain 100 billion solar masses and distributed gas. This is an immense overvalue compared to what is observed. Observational restrictions expected that this gas must be ionized, otherwise, we would have already viewed it. The gas procures high velocities when it comes into massive galaxies. It must agitate and heat up to almost 10 million Kelvin. At this temperature, distributed gas glows in X-rays. X-ray views of nearby massive disks, such as the Sombrero Galaxy, detect only around 1 billion solar masses and hot gas in the growth area. The only explanation appears to be that supernova heat has forced most of the gas toward the exterior galaxy. This supernova warming produces winds, and, certainly, such super winds are located throughout the Milky Way-type galaxies. This is confusing from a theoretical view because supernovae are deemed inadequate for driving a mighty wind from the gravitational potential well of a massive galaxy. Also, at least one instance is an extensive X-ray halo around a model extensive spiral galaxy. In this case, gravitational increase and crash heating produced the most dependable source for warming the gas. The position for the Milky Way galaxy is complex because the local group, which is the regional aggregation of galaxies controlled by the Milky Way, in the Andromeda galaxy, presents a potential defense against the gas required. An illustration of the absence of halo. Gas in the Milky Way may rest in a complicated history, for the gas ejection plays a crucial role. One possibility is that large amounts of gas were dumped into the local group. Into galactic medium, this could not have occurred recently given the power of the Milky Way gravitational field dismissal. However, could have occurred long ago when our galaxy was raised from merges of several smaller systems. Expulsion of gas must have occurred to some degree. During the construction phase of the Milky Way, winds were quickly forced from the star-forming dwarf galaxies that merged into the Milky Way. Some of those construction blocks reside in the halo. As low surface illumination, fossil remains to further confuse matters, we understand that the merging story of our galaxy itself included dwarfs that we are yet gas. Rich star development and improvement transpired through the merging process. We understand this because the chemical bounties of the nearby dwarfs exhibit similar courses as the Milky Way. Halo stars, which suggest that a cosmic relationship endures between the wealth of elements, such as magnesium, and that of iron. There is one variation. However, the dwarf chemical abundances are frequently accounted to reduce metallic cores. Probably, then dwarf composition happened earlier than disk and stellar halo configuration. Much of the increased gas eventually appeared. The disk of 50 could understandably have been discharged by supernova-driven winds from the dwarfs into the intergalactic medium in nearby dwarf starbursts. We, indeed, find that the wind mass expulsion rate is like the star production rate, more commonly low covering brightness. Dwarf galaxies are universal. Supernovae can remove much of the primary gas content. However, this gas must be deflected by growth. Otherwise, these systems would not lie on the perceived trend that correlates with completing stellar and gas mass. The rotation speed of the system, known as the Thule-Fisher relationship, surprisingly the low
exterior brightness.
Dwarfs are in the same relationship, as more extensive disk counterparts on rich star-deprived dwarfs are imperceptible. Regarding the Thule-Fisher relationship from their gas pressure, this indicates that there must be a plot connecting stars to fair proportion and stellar surface density of the disk. Gravitational equilibrium demands that the previous should grow as the latter is degraded. One interpretation associates this link to a variation in star production efficiency induced by supernova feedback, although no model has been produced. Early type galaxies control the luminous galaxies to the end of the light scattering of galaxies. It represents an exponential cutoff, with a unique light of 30 billion solar luminosities in the accepted cold dark matter. Nearly 90 of the baryons are directly in the intergalactic medium. These baryons compose a large gas reserve, probably open for recreation onto galaxies and ultimate star formation. Nevertheless, gas cooling and actual amounts of star development are not discerned for vast galaxies. Most are red and dead, and genuinely all-star formations stopped a Hubble time ago. More commonly, it is thought that extensive spheroid development is discontinued by the forces of active galaxy outflows on the halo gas storage. Much of what arrives in must go back out. Outflows from active galaxies fall, removing the halo of gas and directly relate to ancient and red ellipticals. There is a related gas cooling dilemma in galaxy clusters. Cluster galaxies are predominantly ellipticals, particularly in their hearts, but clusters are abundant of hot intergalactic gas that unavoidably cools and their cause gravitational collapse originally keeps the gas hot. But once the cluster forms, this heat supply is broken, gas inescapably chills down. Once the heat source is switched off, according to speculation, the gas should fall into clumps that become galaxies, creating stars and becoming blue. Nonetheless, we do not see this occur. something is presenting late heating and holding the cooling down if delayed warming is expected in part to gravity cold fall galaxies could not occur. These results may be sufficient to explain light quenching of a star formation by overcoming the cold gas supply. In contrast, active galaxy discharges provide temporary as well as moderate suppression of star production. There is a different way to solve light quenching. We can ask whether the various low lights active galaxies we observe might hinder cooling flows in galaxy groups somehow. It must prevent the gas from building stars in large numbers. Low-light active galaxies may heat the gas, but cannot be discharged via winds. Therefore, one presumes the halos of heavy galaxies to have a massive scattered hot gas relative to the stellar mass. From an observational point of view, our thoughts of massive ellipticals show a baryonic shortfall within the halos. Of these gatherings, however, the baryons are unquestionably near group scales in intracluster stars and distributed gas. Moreover, the gas is enhanced, which gives an indispensable piece of data about its history. Enhancement of the gas by supernovae must have transpired. We understand this from this circumstantial evidence. Reasonable, the gas was expelled by vital supernova input. Most likely, in the beginning stages of galaxy development, in the state of the ellipticals active, galaxy outflows can provide the energy source. Nevertheless, these are unavoidably connected with robust star production activity. Perceptions of ultraluminous infrared galaxies. The brightest galaxies in the cosmos indicate winds in these galaxies. Most of the stellar mass has now been gathered. Nevertheless, they have light above 100 of our Milky Way galaxy. Star formation. Identical star formation speeds are as high as 1,000 solar masses per year. When we recognize such aspects, we likely see the final stages of ellipticals. Information. Indeed, heavy winds are virtually ubiquitous in ultra-luminous galaxies. The flow rate is usually relative to the star production rate, hinting the volume of ejected baryons is like that residing in stars. What is less apparent is whether the high performance needed for massive spheroid formation, previously in place by a redshift of 2, is enough to the position of active galaxies in triggering star arrangement. Star development timescales as short as 10 million years are gathered from large elliptical galaxies. Star development timescales are defined by synthesizing the diverse types of stars required to consider for the detailed spectrum of the galaxy. We can understand from the colors and impact if the galaxy is young or old. One hint to the configuration is that current galactic cores are present in a meaningful section of the total amount of ultra-luminous galaxies. Regrettably, there is a chicken and egg type of dilemma. Here the overlap does not tell us whether the existing nuclei are a trigger or a result of the ultra-high rates of star development. Either way, something is required to expedite star formation, and supermassive black holes are a feasible element. Active nuclei believably play a double role in the spheroid form, both in triggering and increasing as well as in quenching star configuration. A strong argument can be given that feedback, the transfer of stock between different revealing objects, performs an essential role in galaxy development. Unluckily, we do not have sufficient comprehensive information to reproduce in computer models the exact feedback mechanisms are at play when galaxies form. Our measurements, however, show us 3 sorts of activity on the merges of galaxies. The dynamics of supermassive black holes and supernova disorder. When the merger of 2 or higher galaxies takes site, it pushes gas into the center of the other massive galaxy. Thus, one finds evidence for merging, and many ultra-luminous galaxies, gas-rich mergers, plausibly drive the spheroid star configuration mode. However, there are not enough critical mergers, especially at high redshift, to consider all ultra-luminous galaxies also gas-rich. Mergers form ellipticals with distinct morphological properties suggestive of embedded disks because the gas obtains angular momentum, some of which is maintained by the recently formed stars. We solely do not see this outcome in the various extensive ellipticals. They could not have developed this way. Minor mergers are apparent in the classic gas supply method. The gas supply also feeds the middle supermassive black hole. Supernova cannot estimate outflows from massive galaxies. The thermonuclear outflows play an indispensable role in quenching star establishment. Otherwise, various ellipticals are too bright and too blue. Active, nucleus-driven currents are a natural result. Supermassive black hole extension is in condition with galaxy formation or, at least, with the global star production rate. Our second case of feedback originates from supermassive black holes. They are served through the gas-rich state of galaxy configuration. The relationship of supermassive black hole mass with the spheroid potential implies that the development of both is contemporaneous. The starburst association with spheroid formation happens during the supermassive black hole growth period. Active galactic outflows can also trigger star formation before extinguishing it. The marvels are most probable causally related, but we do not grasp the associated arrow of time. Does supermassive black hole extension reseed and trigger the spheroid formation of a supermassive black hole growth and outcome, an ultimate terminator of spheroid formation? In the gas-rich development phase, the energy input from active galactic nuclei is prevailing by direction of magnitude or more related to information from supernovae. Indeed, supernovae provide adverse feedback in galactic disks. They push from possible origins of low-mass galaxies. Supermassive black holes create outflows that present actual feedback, and large demonstration spheroids blow out transpires accordingly, and star configuration terminates when a supermassive black hole approaches a critical mass. That depends entirely on the spheroid mass. The supermassive black hole quenching theory channels to a supermassive black hole spheroid speed dispersal correlation that implements the observed relationship among the black hole and spheroid mass. In both, incomplete condition and grade. Finally, the great explosions of supernovae and other active galaxy outflows play crucial roles in how feedback points to galaxy configuration in disk galaxies. Supernova remains self-regulate. The interstellar medium encouraging fountains out of the disk, the gas chills in the halo, and eventually accretes on the disk as high-velocity clouds through spheroid configuration. The center's supermassive black hole growth period results in discharges that induce stimulated star configuration. The induced supernovae can force winds even at the beginning stages of spheroid generation. Only when the supermassive black hole achieves its final mass is the existing galaxy wind powerful enough to wipe out the spheroid and eliminate all following star form as noted. We do not have a vital mechanism in computer simulations to explain feedback. The situation is particularly grave and not possessing data to explain the forming of the spheroid. Overall, here one needs the overall disk gravitational uncertainty that sets the exhibition for star establishment in disk galaxies. For instance, this restlessness drives spiral density waves that, in turn, create molecular cloud networks. The next steps include cloud fragmentation and commotion generation. This process climaxes when the cloud nucleation fails and stars are created. Our knowledge of these progressive steps includes as much phenomenology, particularly our observations as theory. Indeed, our modeling results depend solely on the phenomenological data. For instance, while supersonic disturbance is perceived to manage on all scales of the interstellar medium, what motivates the confusion is discussed between large-scale gravitational fluctuations, magnetically induced fluctuations, supernova bursts, and protostellar currents, which are all supposed to play a part. Most convincing of all, these climactic events in space present information. At some level, to disturbance over a wide assortment of scales, the product should be indifferent to the features of the input. If not, our patterns would be complex. Maybe the most critical issue is that whatever mix of physics is related to the feedback issues that we observe in the nearby cosmos, there is little incentive to ensure that a similar prescription continues at early interventions in the cosmos. Thus, all forecasts for the raised redshift cosmos, that is the initial cosmos, should be viewed as at best guided guesswork. Is dark energy meriting as the main aim in cosmology? This issue, in turn, is driven by a different one. Will we always possess a basis of dark energy on a different functional level? Given that we occupy a galaxy, will there ever exist a significant theory of structure development? While one can forever find inflationary patterns to explain whatever, sensation is interpreted by the flavor of the month. The general forecast associated with most of the inflation models have had two enormous successes. Nowadays, cosmology seems somewhat unexciting. All judgments converge on the conventional cosmological standard. With its hypothesized components of dark matter and dark energy, inadequately recognized future investigations focus on reducing the prevailing error bars, with the opportunity always lurking to find new signs of physics. Confidence that we have got the final answer requires enormous hubris. Given our woefully incomplete mastery of the first example of the Big Bang, the terminal hypothesis of cosmology will undoubtedly carry our official cosmological model as a component. Time travel. Could we ever justify any of these theories? Does the multiverse hypothesis assert that many words exist only by judgment? Can we hope to question their presence? We require to go beyond our best play to assemble a time machine to progress into another cosmos. This is far out of sense. In terms of everything, we are currently proficient in doing time travel between cosmos. Is a genuinely exclusive goal to get beyond this? We first would require comprehending time travel within our perceptible cosmos. Let us state first, no basic law of physics prevents time travel. Success is, unquestionably, a topic of technology. Regrettably, we are far from the idea, let alone creating a prototype time machine. Nevertheless, let us apply our imagination. Stimulated by the theory of gravity, time travel is likely in principle via wormhole technology. A wormhole subsists. According to Einstein's theory of general relativity, it is a tie into different parts of space and time which can reach another cosmos. Of course, we have never identified a wormhole, but this must not prevent our considerations after all. Most of the cosmos is unexplored. Time travel is the unique way to examine the multiverse theory. We require to go there. This may be and probably is the realm of science fiction, but the rules of physics do not eliminate it. Moving far in space constrains travel, and time-space-time constitutes the fabric of the cosmos. We cannot divide the two, time and travel, that can be defined in the setting of physics. It is a fundamental precursor to moving across the universe. However, a journey in time involves clear inconsistencies that we demand to defy. It would not be a great idea to travel back in the past and eliminate one's great-grandmother for any alleged sin. There is an inconsistency since we cannot alter the present. One answer is that invoking quantum ambiguity permits us to bypass this paradox. One can confirm this by thought exercises. On the quantum scale, let us assume we can burrow into space by creating a tunnel like a train tunnel, boring into a mountain. The substance of a space-time tunnel would require to be especially strong to stop it from falling under the influence of the neighboring space, with its material and energy fields. Nevertheless, such a substance is no different in energy from what would be needed for a spaceship to start. Within the border of a black hole, a course that may be needed to find the most related wormhole, shooting particles into such a hole through space-time would occur in their appearance at an intrinsically unknown location. In space-time, the chances of meeting themselves on the way back would be imperceptibly small, so they could not be beaten off course on the way into the tunnel. Whether there is visible communication is not grasped, but seems reasonable. One would, nevermore, find one's great-grandmother. She would be covered in a cloud of quantum indecision. We all deprecate past mistakes. What would we not give to have another opportunity to return to that little contact with a person who never seen reason, or to retake that important examination, or for those annoyed by recent tourism opportunities? Why not a detailed safari for Tyrannosaurus Rex, or a walking trip of the original 7 wonders of the world? Physics states that all of this and more is plausible, not today, neither tomorrow. But such events lie within the bounds of physics. Here is the procedure for the tunnel. Create a wormhole. This bizarre object, prophesied to survive in Einstein's theory of gravity, is a tunnel through space and time. It is only obtained through a black hole. So, no answer is possible without breaking the laws of physics. Nothing can leave from a black hole. Quantum gravity, the latest hypothesis that unites gravity and quantum theory, and is the holy grail of particle. Physics claims that small black holes and wormholes live throughout space. However, their continuation is short, and they pass before we can take or even detect one. The void is thought to be leaking with such brief-lived abnormalities. Wormholes are there to be found if only we understood how the trapping, though, can be done without breaking laws. It simply requires acquiring a very stiff substance that opposes gravity. Virtual wormholes should subsist for temporary instances. According to quantum gravity theory catching, one would require unimaginably powerful forces. Entering one may be severe. It could cause against itself. Our safest bet may be to find a vast spinning giant black hole. Many numbers of massive black holes are known, often sneaking at the centers of galaxies as one contemporary astrophysical theory. Even our Milky Way actively suggests that all black holes revolve because most huge stars are spinning quickly. These stars are the ones doomed to form black holes. A few will arise to reach beastly dimensions. The one at the heart of our galaxy measures 4 million solar masses. Only if the closing stages involve rapidly spinning matter can one understand how to find a wormhole. A quickly rotating black hole has a twisted event horizon. Typically, the event horizon stops the random observer from reaching the central singularity. An event horizon is impossible for the external observer. Time crumbles to a standstill. Nevertheless, with rotation the singularity becomes easy. It can likewise be visible with no protecting. Event horizon. One can reach one of those and attain the primary irregularity where a wormhole might be for the amateur explorer. The technology for a spaceship to survive entrance into the event horizon of a black hole needs material of incredible durability. As one progresses, the event horizon, the tidal strengths become immensely strong. Any recognized element would be torn to shreds, but adequately stiff material should endure at least in principle to outlive the journey. Indeed, the matter in a neutron star has the necessary strength to withstand being stretched apart by gravity near a wormhole. Constructing a spaceship out of such an element but is on fantasy now. But science fiction has a practice of becoming a fact. Behold the writings of Jules Verne and H.G. Wells. Even stranger material that counters gravity is in deeply diluted form. We call this the dark energy. That is accountable for the perceived acceleration of the cosmos. Time machine technology would ask us to control this force, use it to prop open a wormhole before it locks up, and stretch up the wormhole to a large enough hole for the courageous time traveler to leap in and fade from clarity. Of course, going back to the position where one initiated out would produce an additional difficulty to our fearless voyager. Nevertheless, possibly they are only too willing to jump to new horizons. Mainly, if there is limited choice, at least one scientific obstacle must be surmounted. Firstly, the hypothesis implies that once a wormhole is initiated, it would quickly accrete material and fold in on itself, factoring in a difficult challenge to our ultimate wormhole engineers. A more solid strategy might be discovering a pre-existing wormhole in the center of a rapidly rotating black hole. Technical issues aside, this type of time travel is our safest bet for the investigation of space-time. Regrettably, it is far afield from any technology we can directly perceive. Filed by the American academic Michio Kaku as advanced technology of Type 2. Such technologies are obtainable in possibly 1,000,000 years without breaking any of our cherished concepts. When we speculate about the future, the words of the old natural philosophers give some outlook. Roman philosopher Lucius Seneca died sucker at 65, for instance, and wrote in his Essential Questions, Book 7, "The moment will come when careful research over long terms will lead to light matters that now lie hidden." A single lifetime, even though solely devoted to the sky, would not be suitable for studying so vast a topic. Hence, this knowledge will be released only during long succeeding terms. There will reach a point where our descendants are amazed that we did not understand things that are so simple. To them, many revelations are maintained for ages, yet to come when the thought of us has been obliterated. Our cosmos is a tiny little event, unless it has in it something for each age to study. Nature does not share her secrets. Once and for all, humanity has controlled high-level technology, as we now conceive of. Its growth has been teetering for less than a century. We have joined the department of what the classical Greeks ascribed to the gods. We have mastered flying robots and space journeys, achieved virtually immediate video conference at vast distances, and managed discharges of virtually limitless power. Imagine what we might be able to perform in a century, in 1,000 years, or 1,000,000 years. It would be a foolish person who declared that our knowledge of physics prevented our capacity to master a time machine. On the other hand, of course, contemplate the subsequent cases. Heavier than air flying devices is absurd, stated Lord Kelvin, President of the Royal Society, 1895. If the quantum hypothesis is correct, it implies the passing of physics as a science. Stated by Albert Einstein, anyone who assumes a source of energy from the conversion of these atoms is speaking moonshine, stated physicist Lord Rutherford in 1935. There is not the sparsest evidence that nuclear energy will ever be achievable, stated Albert Einstein. To summarize, physicist Lev Landau states cosmologists are frequently in error, but never in disbelief. We have come a great way since Newton in terms of our knowledge of the physical world. What could we expect in forthcoming decades? Or might we expect a new hypothesis of cosmology? Much of the perceived cosmos already suits into position the grand system of things. However, there is one factor in common with Newton's worldview that ought to provide us a basis for suspecting that we understand all the fundamental physics. Newton brilliantly anticipated, because of gravity, the creation of an almost eternal number of celestial bodies. The force of gravity unavoidably led to uncertainty, and planets and stars had to develop. Nevertheless, Newton could not know in terms of known physics why some things were luminous like stars. Nevertheless, others like planets were not. Newton advanced to a greater authority to resolve his predicament. The physics finding only emerged 250 years later when Hans Peter understood what it took to produce stars that shine, particularly thermonuclear power. The discovery of dark matter models, one of the most critical problems. It is universally confirmed by several sovereign types of investigations, but we have not distinguished a single candidate. This situation has driven some astronomers to challenge the very justification of gravity possibly. The gravity law demands to be altered, then we can dispense with dark matter solely, nor is dark energy in any more reliable state. Suppose we remove the data from supernovae for the quickening of the cosmos. After all, we require a technical model of supernovae. No one could object that using a measuring tool whose ideological foundation is unknown is a high-risk system. There could be evolutionary systematics that simulates the dimming of the most remote supernovae. Maybe intergalactic dust does the dimming, then we would not require acceleration. We know that something controls the mass energy density. 2/3 of it is not gravitating material that changes the large-scale arrangement of the galaxies. It could be something entirely uniform, for example, a new power field. Nevertheless, this appears an even more thorough explanation than Einstein's cosmological constant, which provides all popular data. The situation is curiously suggestive of our conversations about the multiverse and the anthropic origin. Perhaps we require the correct physics hypothesis to cope with the severe restrictions at the origin of the cosmos. There are solely too many issues that occur in our present classification of the cosmos. Buried within these mysteries could well be the roots that give rise to a prospective theory. Fortunately, we are not in a rush. Billions of years of research lie onward, provided of course that humanity does not self-destruct. The Sun will exist for another 5 billion years. It has almost entered middle age by stellar models. There is much we cannot conceive of yet, which may be available on such a time scale. We are on the brink of discovering hordes of Earth-like planets. Many of those will be more mature than the Earth, with a billion years head start. Over Homo sapiens and our culture, one cannot start to guess what culture in some distant galaxy. Anonymous to us might be proficient in manufacturing, of course. This does imply that the development of life is not improbable given the right conditions. We will never be sure of the result until data is found. Our investigation of the cosmos need not inevitably be defined in space and time. We may find a nearby wormhole or plane singularity and utilize it as a time machine. We may improve the technology to be capable of traveling to another cosmos. We will see how the cosmos began. Furthermore, no uncertainty exists that we will begin to conjecture the nature of dark energy and dark matter particles. Supernovas and dark matter. Recognizing dark matter is one of the most critical trials in cosmology. 90% of the material in the cosmos is dark, but we can only conjecture about its nature. The principal candidate for dark matter is some fundamental, weak, elementary particles. This candidate must associate with the matter in the cosmos much weaker than the proton, a primary component of all material. For instance, everyday matter ultimately fragments towards stars. This weak interaction of dark matter reveals its alleged conduct in the cosmos when a cloud of dark matter and standard matter contracts to produce a galaxy. Nevertheless, the mysterious matter is left behind its weak cooperation. also suggests that dark matter particles do not lose power by radiation and darkness during cosmic development. Dark particles consolidate into dark clouds, but not into stars. Dark matter is drawn by gravity alone. In our pronouncements, today we find dark matter both in galaxies' inner areas and outer regions. For example, in our own Milky Way galaxy, there is an expanding collection of dark matter in the inner galaxy, in opposition to how ordinary matter dominates in areas that include our solar system, which is ordinary material orbiting our sun's dark matter. Also, populates the exterior regions of galaxies where there are fewer stars. Dark matter controls the mean density of these outer quarters. Nevertheless, specific stars distant from the galaxy center proceed to manage their orbital velocity. If the stars followed the appearance of the dark matter, the circular quickness would decrease as the gravity field gets smaller. The dark matter is much less intense than the starlight. Dark matter consists of weakly combining fundamental particles. We know that any particle that can survive according to the rules of physics once did live in the fiery forge of the Big Bang. All particles hold particles of the negative charge. Today, antiparticles are remarkably rare. Nevertheless, in the initial example of the Big Bang, each particle is accompanied by its antiparticle. There was flawless symmetry. This increased, however, as the cosmos calmed down. The primordial forge left behind limited antimatter, which is helpful for us because contact between a particle and antiparticle ends in total annihilation. The amount of remaining antimatter depends only on the strength of the interactions of the particle and the subject. Furthermore, the antiproton is actively interacting proton, antiproton pairs already controlled for cosmos. Many were already existing partners of protons, and antiprotons were generated immediately from radiation at the ultimate temperatures found in the first nanoseconds of the cosmos. As the cosmos expanded and reduced, spontaneous creation held almost all at the antiprotons obliterated with protons. Nevertheless, luckily for us, some protons are left to create the material. Cosmos, this significant annihilation, created the cosmic microwave background that we now measure the heat left over from a fireball at the origin of cosmos. The identical philosophy pertains to the dark matter particles that most were obliterated at this period. In our search of the dark side of the cosmos, we sought a remarkable event in how the laws of nature appear to work. This sort of discovery always makes cosmologists feel great. Nevertheless, in this case, far more were left back because certain particles combined so weakly. There was neither reason whatsoever for this. Eventuality. Nature commands it. Weakly interacting particles can value all the observed dark matter. If their interaction strength is characteristic of the weak nuclear force, they need, of course, to be long-lived and associate with a potency like this of the neutrino. This seems a tangible interaction to be required for such particles. The interpretation of the origin of the weakly interacting dark matter soon shifted to more compelling. A new hypothesis called supersymmetry was revealed that postulated the existence of hundreds of potential dark matters. In the new supersymmetry hypothesis, any applicant for dark matter must be a weakly interacting particle. Only one of the competitors can be the proper form. In particular, it needs to be the lightest of the supersymmetric particles to be adequately steady. The remainder of the candidates lives for bare nanoseconds. We are now close to the path of these particles. One of the principal goals of the Large Hadron Collider performed by CERN is to hunt for proof of supersymmetry. The accelerator, which runs for 17 miles, will smash one-sided jets and high-energy proton-antiproton to form collisions. The impact releases energy that in turn produces waterfalls of quarks and other short-lived particles. Force must be maintained in the contact, seeing a stream of particles emerges in one direction with no similar stream spraying out. In the opposing direction would present evidence for supersymmetry. As noted earlier, there are many candidates for dark matter. Fortunately, the most common class of hopeful particles hails from the hypothesis of supersymmetry and is expected to be visible. Granted that supersymmetry is correct, the most graceful supersymmetric particle is supposed to be durable and can judge dark matter density. Supersymmetry is driven by hypothesis, but also by empirical discussions. One of these is the running of the coupling constants of the underlying forces. The constants are vastly distinct from all other today, but this was not the situation. Today, we exist in a low-energy universe, but At very great energies, the weak nuclear force grows much stronger than we extrapolate. The strengths of the various forces included at low 100 giga-electron-volts energies. They appear to gather near 1,000 trillion giga-electron-volts. Supersymmetry needs concentration at precise energy called the order of great combination of the elemental forces. As we observed earlier, this order granted the stimulus and physical setting for expansion again. The applicant particle must be dull and weakly interacting. It is related to the neutrino and is the complex counterpart of a distinguished particle such as the photon. Neutrinos are in thermal stability at the high temperatures of the ancient cosmos. As the temperature dropped at the origin of the cosmos, a relic density of all the constant particles persisted the weak nature of impartiality. No self-interactions occurred in an excellent relic density. In opposition to that, emerging from actively interacting particles, remarkably the relic density generically provides an almost critical density of dark matter for a weak-like cross-section. The cosmos was previously at energies, wherever supersymmetry prevailed and a breeding ground for supersymmetric dark matter. This means matter and antimatter, the primordial forge, must have formed pairs of weakly interacting particles and their antiparticle companions. Particle theory gives us nominees for these particles. None have, however, been perceived, which is a lesser barrier. If one of these distinct particles is constant, then its weak interactions support a significant survival portion. Today, these could be the obscure dark matter. Now we can explain why there was so numerous dark matter particles left over from a single Big Bang. We are attempting to obtain this dark particle by utilizing heavy machines using state-of-the-art technologies like the Large Hadron Collider, but this scheme alone costs 5 billion euros. There is another 5 billion euro upgrade in 2021. The collider has put thousands of superconducting magnets to create a particle accelerator 5 miles in breadth in its circular ground design. A device like this can grow so precious that we reach the physical limit for such analysis. Fortunately, therefore, we can still use the cosmos itself as a particle accelerator. In the expenses of the cosmos, particles are destroying each other beyond space. Consequently, we are attacked with dark matter. About 10 million particles per square meter per second pass within us. As we will shortly see, we do not have to create a super collider. The cosmos itself presents a poor man's way of hunting for dark matter. The dark matter that besieges us is created by the annihilation of particles, as if diving into a super collider in the faraway cosmos. How is this an attractive place? Once in the incredibly early cosmos, the dark matter particles were far more diverse and annihilators were common. Today, their density is moderate and annihilations of the dark matter particles are unique. Nevertheless, although rare because the capacity of all galaxy halo is so vast, annihilations may yet lead to a detectable sign. Consequently, our best method is the wreckage from particle annihilations. Conventional particle masses are supposed to be on the order of the power scale defined by our current supersymmetry hypothesis. This system is between 100 and 1,000 proton masses. The acronym for these weakly interactive massive particles is WIMPs. While annihilations take place, they create a shower of energetic elementary particles, most of which decline quickly. The tangible outcomes are high-energy gamma rays, proton, antiproton pairs, neutrinos, and electron-positron pairs. All of these are probably discernible with future operations. The prophesied flux depends on the density of dark matter. We assume the regional density in a solar neighborhood from the revolution of our galaxy. It amounts to 1/3 of a giga-electron-volt per cubic centimeter, around 10 million per square meter per second pass through the Earth. With such a notable influx, we can attempt to identify the particle's indirect discovery procedures directly. This tremendous flux of weakly interacting particles illustrates the quality of the research challenge for the prospect. The dark matter particles, although very weakly communicating, do irregularly collide with atoms in a machine. The detector has a bizarre sensitive matter to pick up a slight trace from particle contacts. Nevertheless, this through detection does not operate with other sorts of dark matter annihilation. So, we practice secondary detection as well. This technique picks up the irregular dark matter annihilations in a galaxy halo. When these annihilations happen, they create an energy loss in the style of both gamma rays and energetic particles. Indirect evidence of dark matter. Our discovery of these as indirect evidence of dark matter Both varieties of detection provides us hope to determine the dark matter problem. It is also a charming story of method and technology, so let us examine more closely both procedures. Beginning with direct exposure, there is no replacement for direct exposure of the dark matter particles. The flux of such particles on the Earth is comparatively large. Of course, the interplays are weak, but stretchy. Recoils leave, possibly, detectable signs and adequately large portions of the target element. The nuclear recoil's energy and irregularly ionized detector nuclei detectable signals involve seeing hints of electrons and ions and oscillations of vibrational energy in the atomic lattice arrangements of all solid matters called phonons. However, there are actual experiences mainly emanating from cosmic rays hitting the indicator and producing neutrinos to see the WIMP signal. So, one has to overcome these experiences. The only way is to go far under this used areas. In mines have been applied. One of the most useful is in Sudbury, Canada, at a depth of 3 kilometers, until lately detectors in clandestine laboratories have been kilogram scale, with sensations to elastic scattering cross divisions down to a 10/1000th of a barn or a 10 to the power of -24 centimeters squared. 1 baryon is the regular interplay cross-section for average atomic nuclei such as protons. It compares to a valuable area for scattering and mounting in the square of the standard radius of a proton. These are the continued nuclear interplays for a meaningful density of WIMPs bearing from the real early cosmos. The regular cooperation strength must be less than a billionth of a barn. This is the area of weak nuclear interlace. These are the results that include neutrinos. The experiments have directed out WIMPs in this regime. Nevertheless, the supersymmetric model parameters provide a notable dark matter mass over a wide range of interplay strengths below regular weak interactions. If dark matter cross-sections one can own up to the 3 orders of magnitude deeper than current test destinations from WIMP searches, the opinion has shifted the goalposts and more delicate experiments are demanded. The only way ahead is to have more enormous mass detectors. Each ton or even kiloton detector masses are expected to examine the complete range. This is the intention of the new age of trials that use detector matters as varied as liquid argon and xenon or crystal germanium-1. Exciting addition realizes that dark matter may control fine-scale construction on the solar system scale. The dark matter is cool because individual particles have substantially no random motions. If fluctuations are started initially, the dark matter answers to gravity on scales much less than these of galaxies. Most small clumps are supposed to have Earth masses but are greatly more distributed than a planet. Consequently, the Earth as it encircles the Sun hardly runs into dark matter clumps. Dark matter is so diluted that it has no immediate control via influence on the Earth. However, investigations searching for the weak sign from immediate exposure would find an annual inflection of the tricky signal streams of dark matter in the solar community. Emerge from the unfinished tidal separation of dark matter, masses in galactic orbits won through exposure experiment at Gran Sago. A deep secret laboratory in Italy uses this designation and is the only test to report a claimed exposure. This venture, called Libra, employs a vast vat of sodium iodide and hunts for light and deletions. Other groups discuss their results, however, using different techniques and more sensitive experiments. A window lives if the neutrinos interact coherently. In this case, the interplays depend on the regulation of spin of the end atomic nucleus, which can be essential for nuclei. With odd numbers of particles, sporadic experiments are susceptible. To this synergy, the most critical problem is hydrogen. The Sun contracts such WIMPs, and its composition is very lightly affected. If the volume is around 5 proton masses, the WIMPs take a long period to settle into the heart and obliterate. The general lower gas on WIMP mass is about 50 proton masses from accelerator limits. Nevertheless, some designs permit these more moderate masses. Low-volume WIMPs turn out to be a potential means of mitigating Libra. With most other analyses, there are 2 methods for estimating the interior temperature in the Sun. One includes identifying the neutrinos released in the thermonuclear responses that occur in the solar core. The growing detection of solar neutrinos has proved that thermonuclear burning of hydrogen commands the Sun. It also stays at the central temperature to great accuracy. Another test involves identifying seismic quakes in the Sun. These WIMPs scatter with cosmic particles and somewhat alter the temperature profile by redistributing the thermal energy helios. Seismology measures very slight fluctuations of the sun. The frequencies of the standard methods depend on the sound exchange time in the sun and, hence, on the temperature form at present. Our most suitable model of the sun cannot consider for the helioseismology issues. The difference is only about 10%. However, the result is that despite the sun being the nearest star and exquisitely well examined, we yet lack a comprehensive knowledge of its composition. Dark matter may conceivably have a part to perform, although it is considerably more likely that the difference rests in something as ordinary as our modeling of disturbance inside the sun. As we explained earlier, our detailed disclosure of dark matter is achieved by tracking the pieces that spray off other particles when they conflict with dark matter. When dark matter particles of 100 to 1,000 proton masses conflict with other particles, the annihilation provides energetic gamma rays, neutrinos, positrons, and antiprotons. All of these are distinguished signatures that can be discerned upon a known framework. High-energy positrons that appear from collisions, for example, are particularly beneficial since they are a rare segment of the galactic cosmic rays. Moreover, all these byproducts of the impact look distinct from remains of the dark matter, since those remains cannot exceed the WIMP's mass. This diversity leads to a point in the energy frequency of high energy. Photons are particles. Other particle experiences are blind to WIMPs, so the backgrounds do not display any articles that might show the presence of WIMPs. Despite the various competitors for the most vivid supersymmetric particle, we understand it is annihilation cross-section. To high efficiency, this arises from the claim that the WIMPs value for the density of dark matter if the cross-section is too level. There are too numerous WIMPs. If it is too high, there are also few WIMPs. This limitation occurs because annihilations in the entire cosmos made the surviving body of WIMPs. The WIMP particle so far is undetected, which, of course, indicates that its mass is unexplained. However, the supersymmetry hypothesis specifies a series of cross-sections at any provided Massachusetts. This series spans some 3 factors of 10 miles. The permissible mass reach extends from simply 50 giga-electronvolts to 1 tera-electronvolt. The answer is that tests must include an extensive range of delicacies to have any venture of discovery. However, discovery at some level is confirmed if the lightest supersymmetric particle is the companion of one of the perceived particles which, themselves, are arranged according to their rotation and mass into particles. For instance, protons or fermions, which carry electrons and quarks, the positrons, afford a good sign because universal ray positrons are rather limited. The local dark matter density measures the positron flux. The gamma ray flux is also an attractive sign. The halo is clear to gamma rays because the density of dark matter is greater. Near the core of the galaxy, the gamma ray flux is increased. There are gamma rays generated by the interplay between universal rays and interstellar gas. There are also positions in the universal galactic rays, but for dark matter sign should reach out its positrons, and gamma rays have a different combination of energy. Defined by the mass of the annihilating particle, exposure of wastes in both the positrons and gamma rays, corresponding to the associated backgrounds, would be proof of dark matter. Particles tests carried out far away above the Earth's exterior have been conducted to study positron and gamma ray evidence. It is essential to go into space because there is too much corruption by cosmic rays communicating with the Earth's atmosphere. So far, there is no reliable evidence of a signal in either gamma rays or positrons that could be from dark matter. There are though hints of potential exposures in both cosmic ray positrons and scattered gamma rays. For example, high-flying balloon trials reported an unusual spectral bump trait in the positron flux that is not defined by the featureless secondary spectrum of positrons created by cosmic ray interplays with interstellar material. The dark matter particles obliterate into a rain of debris. Consequently, the annihilations generate a positron feature collected around 10% of the particle Massachusetts. However, the information was not persuasive. The possibilities are vital. It is too rash to make much of any potential annihilation sign. New investigations are underway. A new trial on an Italian-Russian space satellite propelled in 2006 called Pamela takes information that presents a much improved determination in the positron flux. After several years in orbit, early proceeds helped the unusual spectral bump, but the interpretation of this article cannot necessarily be described as a dark matter signal. The energy is much greater than anticipated from the simplest speculations. The alternative solution appeals to a nearby pulsar in the constellation of Gemini, called Gemini, an abbreviation for a Gemini gamma ray source that is perceived to be a source of vital energy gamma rays. More data will be required to explain the preliminary results better, and it will be required to find complementary signals. The most encouraging of these arise from distributed cosmic gamma rays. Gamma rays from space ought also to be identified. Indeed, the Milky Way glows and gamma rays are created as cosmic rays crawl through interstellar gas clouds. In summation, high-energy encounters between protons create gamma rays. The Compton Gamma Ray Observatory identified an excess distributed flux of gamma rays from the inner galaxy. The energies of these gamma rays seem to be greater than anticipated, from the flux foretold by cosmic ray interlace with interstellar gas. More unusual, decay courses may be shown than would be possible with cosmic ray protons. This is precisely what is prophesied for the WIMPs. The possible decay channels for WIMP has no annihilation, including extensive quarks. Measuring up to 5 proton masses, the resulting gamma rays from decays of these quarks are more dynamic than those created when protons crash with other protons. First, though, the data needed to be established. The Gamma Ray Large State Space Telescope, named Fermi after Italian-American physicist Enrico Fermi, was started in May 2008 and should implement the required confirmation if WIMPs are the elusive dark matter. The Fermi telescope increases sensitivity by 100 over the prior gamma rays satellite venture flown on the Compton Gamma Ray Observatory. This exercise will significantly advance the current data. It should be likely to confirm or reject the existence of the potential signal from obliterating WIMPs. If the initial proprietary results were to be understood as due to WIMP annihilations, a critical issue occurs. Concerning the power of the predicted gamma ray and positron signs, what has been, perhaps, observed is far exceeding extensive than expected. The quest for dark matter and our quest for dark matter cosmologists also need to battle with two different sorts of sensations that can effectively disclose the ambiguous particle. One of these is the clumsiness of dark matter. Besides a moment, is how dark matter spikes while it is in the proximity of a black hole. There is a resolve to this predicament. At the slightest for the gamma rays, the clumpiness of dark matter is linked to its capacity to provide the earliest design for the detected wide-scale structure of cosmos, which occurs later in the very ancient history of the cosmos. The WIMP particles decoupled from the radiation, which suggests that in the recent past the WIMP particles were freezing. That is, they possessed negligible arbitrary speeds continuing from their thermic origin. As the cosmos developed, random acts of particles would decline, and the WIMPs would grow cool. This is the connection between cold dark matter and large-scale construction. The complete clustering features can be represented in computer simulations if simple models for galaxy formation are used. Nevertheless, the cold dark matter candidate has not, however, been identified. It remains a theory. One ambiguity in computing the flux is the size of the clumpiness of the dark matter. For now, we operate on the premise that the annihilation rate is equivalent to the square of the density. Mathematical simulations of galaxy formation display that halos are clumpy with up to 10% of the dark matter existing in clumps, appearing in a substantial increase factor for the annihilation flux. The theoretical modeling of the halo informs us that it is highly clumpy in a clumpy halo. There are considerably more particle impacts and annihilations than in a soft halo. It is tolerably simple to consider the observed gamma ray flux. In this way, the positrons cannot be readily defined because positrons usually scatter as they propagate in the interstellar medium. The detected positrons cannot come from far away and not from the inner galaxy, where the improved consistency and clumpiness of a dark matter boost the perceived flux. The positron story must be more complex depending on how the positrons produce and accumulate. The flux of the annihilation sign is susceptible to the smallest size, about the size of an Earth mass for typical WIMPs. Nevertheless, interplays with stars will tightly confuse many of the clumps entirely. Depending on their orbits, clumps with orbits highly likely to the disk should remain. Low-mass clumps are barely visible via their annihilations beacon, which is available by the second detection method. We have simply considered black holes shortly so far, but now they have grown an indispensable factor in distinguishing dark matter. As well, dark matter is collected in the region of a black hole. Furthermore, relic bunches of dark matter form around growing black holes. Dark matter particles are improved in representation in the nearby increasing gravity field. Consequently, the dark matter density is developed near the black hole. So, as the annihilation signal, we initially need a summary of black hole generation, their formation needs. Matter that can dissipate energy as it deflates baryons can do this by radiative cooling, except dark matter cannot. So, it appears not to become a matter for the black hole. Nevertheless, as the baryons aggregate to create the black hole, some dark matter particles constantly are deceived by the growing strength of the local gravity field. Consequently, the annihilation flux may be significantly increased near a massive black hole that develops in the nucleus of a forming galaxy. These black holes are supposed to form using the accretion of baryons onto a seed black hole. One that is only growing the seed is produced from the wreckage of massive stars. This is not an exclusive development possibility. Furthermore, a different route to massive black hole production is via runaway amalgamations of stars. We see the phase of black hole growth diffusely as the importance of gas accretion. The luminosity of the black hole progress as it is refueled by slipping debris. We infer the number of fueling considering. This is the aspect that power quasars and energetic galactic nuclei. Finally, we have additional clues regarding how black holes form and their relation to dark matter. One is that supermassive black holes typically show up in the spheroid, our impressive bulge at the hearts of galaxies. This seems to be a cosmic aspect. A large section of the mass of a spheroid is dark matter. When the primary black hole formed, it must have concentrated the confined dark matter. In its proximity, the weakly interacting dark matter returned to the deepening gravitational potential about the black hole. A density spike of dark matter appeared within the gravitational field of influence of the black hole. In waiting for dark matter spikes, we simply recognize that black holes form with a wide variety of masses. Minor, dark matter clouds in which baryons can moderate amount to about 1 million solar masses in weight. The most extensive resemble to giant galaxies. The analogous black hole masses vary from 1,000 solar masses to a few billion solar masses. All these black holes manifest dark matter. Spikes or cusps, black hole mergers, terminate those nearby cusps of dark matter. Therefore, it is unclear, for example, whether the 3 million solar mass black hole at the heart of the Milky Way galaxy occupies such. If this were the problem, the annihilation speed would be significantly improved in the vicinity of the central black hole, and this annihilation time would be detectable via gamma-ray emission. Nevertheless, not all black holes travel to the heart of galaxies. For example, during the hierarchical development of the Milky Way, which included merging clouds of dark matter and baryons, the smaller black holes did not blend into the inner black hole. These intermediate mass black holes reside in orbit in the central galaxy. They are everywhere, and they are possible targets to identify dark matter spikes. Black holes are constantly ejected from the cause of galaxies, possibly into intergalactic space. A merger of two black holes frequently concludes with a one-sided burst of gravitational radiation. The net effect is that the merged black hole experiences a kick. In the reverse direction, since momentum is conserved, the obtained velocity is often open enough to dismiss the black hole from its host galaxy. These intergalactic black holes should retain some dark matter in their environment. Although merging tends to minimize any initial spike of dark matter, the spike should last around intermediate mass black holes that have not been known to merge. These 1,000 solar mass black holes are evidence of the original clouds within the earliest stars that appeared. The most extensive of these clouds would have frozen as they emitted radiation from hydrogen, atoms induced by encounters with other atoms. This, so-called Lyman alpha, remission, and the effective cooling compared with this type of cooling which demands only atomic hydrogen would have aided gas accretion rates and developed protostars. The enhanced growth implies that the first stars were undoubtedly massive. Massive star destruction facilitates the possible formation of thousands of solar mass black holes. The most extensive black holes in the cosmos power up ultra-luminous quasars. These are the most fundamental black holes, and their sizes pass a few billion solar masses. They are found in the initial cosmos at a redshift of 6 or exceeding. These black holes are so extensive and in positions so early that intermediate mass precursor black holes must have survived. To explain their development, These intermediate mass black holes could be the lost link between primordial clouds, actual, ancient states and quasars which develop later throughout the most central black holes. As noted, regrettably most of these more miniature black holes failed to blend into the bigger ones, and so are leftovers in common. The merging manner is notoriously unproductive. Anyway, many smaller black holes would be discharged by recoil. In the formation of binaries black holes, in orbit, about each other, and then quickly be disintegrated. As the more extensive systems progress, nevertheless, as many leftover black holes survive, then are destroyed. Furthermore, these are the remaining black holes that we believe populate our halo. These intermediate mass black holes are assumed to value as much mass as the interior supermassive black hole. In the galaxy, most relevant for our purposes, here these intermediate black holes maintain their original dark matter spikes. Thus, these black holes are prime candidates to consider for gamma rays and neutrinos created by annihilations of the dark matter now in the form of spikes. Furthermore, if seeing and identifying dark matter is not challenging enough, cosmologists are also engaging with dark energy, and with more surprising findings, the role of observers is cosmology. A philosophical science, cosmology unavoidably leads to tolerances that possess philosophical and even theological overtones. Inescapably, a cosmological hypothesis is defined with why human beings live in this unique universe and our role as witnesses. After all, if we did not endure, who cares? The physical models of the cosmos have sufficient chinks in their armor for these thoughtful and even metaphysical questions to compress through the rifts for centuries. The universal answered, a human survival, has implied that we are more than an occurrence in the cosmos. In recent decades, this approach generally has been named the anthropic principle. Such concepts are very compelling for theologians. Of course, the anthropic method has also been captivating, if not completely impressive, to philosophers. For cosmologists, however, this can often be a troubling area to start. In science, we try to stick to data. We try to describe the natural origins of things according to laws and principles. Indeed, we wish to demonstrate by physical law and theory what contrarily seem to be unique accidents or events. One of these is the beginning of human life on a planet some 14 billion years after the Big Bang. Galaxies, stars, and planets did not significantly have to exist. Nevertheless, they are making our continuation possible. The scientific project of defining our behavior has been around for quite a while over the centuries. We have fought our way from a geocentric cosmos beloved by the Greeks to a heliocentric cosmos founded by Nicholas Copernicus. We have called the notion of our non-locality in the cosmos the Copernican principle, for reasonable ideas up until Einstein's time. The Milky Way was used to be the complete cosmos. This resolution was overcome by Hubble's pioneering determination of the distance range of the cosmos. It became apparent that our Milky Way remained a run-of-the-mill galaxy, neither great nor small, but depressingly familiar about the whole cosmos. The non-special situation of our environment has been called the source of mediocrity. Our changing view of the Milky Way galaxy shows how we came at this knowledge of our averageness, familiar or not, and cosmologists still wrestle with our continuation. To settle this issue, we need some guidelines for commonality. Otherwise, we could suggest any bizarre cosmos and fall over the border into science fiction. The most straightforward way to start is by being down to earth, inquiring about our physical reality. Concerning physics rules, we cannot rely on gravity and biology to justify our reality. Concerning the entire cosmos, when cosmologists rely on the anthropic principle to justify why we exist, most use a limited version while a minority use a fixed version. Cosmologists uses the limited version. We simply assume that the cosmos is the way it is because we are here to witness it. This is a tautology, a circular argument, but it nevertheless has some advantages. For some solutions, this approach allows the presence of the so-called multiverse, in which many potential cosmos exist, that are unwelcoming to our presence. The most advanced assumptions of quantum gravity count extraordinary 10 to the power of 500 realizations of potential cosmos, all separate from each other because there are many necessary constants of nature differ. On the one hand, given the unbelievable collection of alternative cosmos in the multiverse, it grows remarkably doubtful that our perceived cosmos should even exist. Nevertheless, it does exist. Furthermore, according to the weak anthropic law, our living has simply selected the precise cosmos. After all, we can simply recognize a cosmos of a particular size old enough for stars and planets and life to have occurred. Nevertheless, is this sort of conception of physics, or is it metaphysics? Because of our continuation, the age of the cosmos must be old enough to provide stars to synthesize carbon, the foundation of biological life. The next reasonable step is to point to how the uses of all the significant constants of nature, which may diversify throughout the multiverse, are defined by the necessity of our presence. Another path to the weak anthropic principle favored by many of my coworkers selects only the tiny subset of so-called pocket cosmo within the multiverse, and this pocket allows galaxies to form and life to develop within these little pocket universes. The expectation becomes vital for scientists seeing only a little, but non-zero value for dark energy today. A sturdy variant of the anthropic principle maintains that life is determined somewhere in the multiverse. Nevertheless, these reliable anthropic discussions are undercut by forming a possibly infinite age for the cosmos, which insinuates that the cosmos expands and contracts forever. Furthermore, we simply observe one of the developments. Much can follow over a long time, and a cosmos that forever renews itself via eternal expansion. In all anthropic disputes, proponents attempt to demonstrate the relationship of human survival to the values of the primary constants of nature. There are, at least, three rival theories on how these conditions came to be. The first assumed a grand designer could have chosen the values. This has great interest to proponents of the intelligent design of the cosmos. Most cosmologists argue emphatically that there is no obligation to entreat such a theory, although eventually it decreases the problem to a question of individual belief. The second option advances to currently unknown physics. For instance, we notice those general laws could surmise the height division of human beings. Perhaps we only do not still know the laws for traveling in the multiverse. It may be that it takes an endless time to populate the wealth of panoramas rolling underneath the hill of a false vacuum. We possess no reason to speak about the possibilities of our cosmos, appearing the cosmos began in a steady state. It was the expansion, afterward, that produced the profoundly asymmetric state of material encompassing us. The assumption is that it would take so long for a void to produce this cosmos that it would appear only once. The possibility question is unnecessary. The third option, and to my judgment the most suitable analysis, says that there was no choice at all. We are here because we are hereabout. This is what must result in an endless multiverse. Some versions of quantum gravity attracted to the complexity of the first conditions to support an infinitude of landscapes and cosmo in the multiverse. If this remained the case, the competition and the conundrum are over, the dice were thrown, and our cosmos was determined someplace in the multiverse. Furthermore, here we stand. Are we individual? That is a different story. Although an endless multiverse cosmos would provide an infinite amount of cosmos like ours, just as an absolute cosmos provides infinite number of stars, planets, and paths of Earth, one can mainly test this theory. Future investigations will measure the shape of space with impeccable accuracy. If the curvature differs from flatness, an ever-expanding cosmos, we will presume unparalleled in human thought. A somewhat closed cosmos would show the finiteness of the area. A somewhat open cosmos would go far near demonstrating that time is infinite, at most limited. In the most common cosmology, this did turn out to be the problem. One would no longer need to request any anthropic principle, Darwinian division, or constant expansion. Some cosmologists undecidedly say that the anthropic principle is not yet consistent from the root. It is entirely irrelevant. There is no way to verify how the cosmos might change if we did not exist or match our universe. This is the spirit of American quantum cosmologists, for instance. As an option, he settled cosmic development like the Darwinian belief in biology, given the massive multiplicity of cosmo. Maybe there is a means of natural selection by which one cosmos becomes approved to explain the evolutionary system. Cosmology engages in black hole formation to spawn new cosmophysics, does not prevent this process of new cosmo from popping into reality. So, therefore, we are obliged to theorize that it may happen if it does transpire. Rich black hole formation offers a potential channel for cosmos production. In this proposal, the winner in this universal race that is the most likely cosmos is overflowing with black holes. Our cosmos is not far from this situation. We understand that 1% of baryonic material is in the form of extensive black holes. At the most limited point, 0, these per se are not perfect for cosmos production as they ordinarily are very long-lived. It is their ancestors that might contain the mysteries of nature. It is even thought that the elusive dark matter is in the formation of black holes, in which one has a cosmos whose black hole content produces more than 20% of its mass energy content. The massive black holes could be either recognized byproduct of the ultimate nature of a black hole that governed for cosmos. Black hole birth may give a physical means of universal natural preference. However, the underlying assumption that migrating black holes might produce cosmos is highly uncertain. For instance, tiny black holes are believed to evaporate. The smaller the black hole, the more prominent the deflection of space in its environment. If a black hole weighs fewer than the mass of a mountain, something like 100 billion tons, the framework of space near its exterior is ripped apart and the black hole ejects out mass. It vanishes. Such tiny black holes are described as mini black holes, and short-lived mini black holes ruled the universe. At the Planck instant, singularities are at the heart of all black holes. These are possible gateways to different cosmos. Nevertheless, it seems doubtful that many black holes would result in relic universes. Somewhat all the data once included in the black hole is evaporated along with its size. A chief rival hypothesis to this birth by black hole scenario is the concept of eternal expansion of the cosmos. Inflation can replicate itself. It can occur again and again. That is because the quantum hypothesis tells us that the most unlikely events can happen if we wait long enough. Furthermore, if the cosmos is large enough, such unusual events must transpire someplace. So, the distance can begin wherever at any time in an infinite cosmos. This is eternal expansion that suggests we are not in a particular place, but our perceived cosmos is remarkable. It is the ultimate successor to the Copernican principle. You may investigate whether there are any results of continued enlargement. One of the most remarkable inconsistencies in cosmology is that the universe is dominated by dark energy. All we know is that the universe is quickening and this unknown energy force is governed. Recall that it was first considered to endure by Einstein to stop the cosmos from falling before the expansion was seen. However, the expense of dark energy is insignificant. The quantum gravity theory applied to cosmology foretells that the presence of this small force is deeply unlikely. One answer is that many cosmos are presented by hypotheses like persistent inflation with all probable values of dark energy. Ours appears to be where galaxies and stars could form dark energy, where outstanding stars could not appear. Gravity is negligible compared to aversion. The other cosmos were too scorching or too frozen or too dense or too light. Is there a multiverse? Theoretical physics engages with the concept of a multiverse, the organization of an infinitude of universes, including our local achievement, which is a fantastic concept. Is it even in physics to assume the presence of a multitude of coexisting but non-communicative cosmos? There are many hypotheses for the beginning of a multiverse. Still, it is a poor reflection on our modern state of knowledge that none of them are any more reasonable than that connected to a commonly cited older woman who reached up at the end of a talk on the nature of the cosmos and angrily accused the distinguished speaker, American philosopher William James. She declared that our Milky Way galaxy rests on the back of a giant turtle. This is in fact an old-fashioned Hindu myth. Furthermore, what praise is the turtle enduring? On questioned an amused speaker, she responded that the solution was evident. There are numerous choices. One is that the cosmos, our cosmos, is individual. It is just that our minds have not yet taken the last hypothesis. For solving this, another opportunity is that there is a multiverse located in all practices of coexisting but non-communicative cosmos. There is an endlessness of choices, but nearly all of these are contrary to the development of life. Too hot, too cold, too bumpy, too smooth, too modern, too ancient, and so on. Consequently, Arizona State University physicist and author Paul Davies has denominated the Goldilocks enigma. Our proximity selects just one cosmos as observers, Such multiverse hypotheses are claimed to be rights. Philosopher Neil Manson, the ultimate resort for the acute atheist more effectively. The underlying physics is inadequate. We certainly have no sense if the many so-called scenes in the multiverse can be populated by Pocket Cosmo, as its citizens are called. The continuation of a bio-friendly cosmos is a hugely remote event that does seem to require an answer. One alternative is to advance to a higher authority or creative design to justify our behavior. This clears up the question of who created the designer and why, nor does it differentiate monotheism from Valhalla, the field of the gods in Norse mysticism. While this resolution is a supported conference stopper for science-minded personalities, the options do not stop here. Possibly, the cosmos is a vast Gaia-like entity named for Gaia, the Greek goddess of strength with built-in awareness of its mission. Alternatively, perhaps, we are dwelling in a matrix-like supercomputer simulation. One might assume that Hollywood came closer to the fact than the most eminent string theorists, whose string theory to reveal quantum gravity. This must not confuse anybody. There is one answer that I find most appealing. Suppose the cosmos was eternal. All bets are off in this instance, because it is reasonably challenging to calculate the chances for or against life in an infinite cosmos. The most extraordinary events occur someplace. Furthermore, here we are in our bio-friendly pocket cosmos. Perhaps, what is most remarkable for the physicist is that this metaphysical solution of an eternal universe can be experimentally testable. At least in teaching, such tests primarily involve reading the abundant angular scale characteristics of the cosmic microwave background and increasing the accuracy of the universe's curve measures. The frontier boundaries of the multiverse. We know the Earth is not flat because no one has described hanging over the edge. The fullness of the Earth restricts its size, giving it a boundary that cannot be bisected. We can take a similar line to the multiverse, a proposal that purports to describe many of the so-called eventualities. In nature, beyond certain borders, in nature drastic changes take place. Many of those changes could be a disaster for human reality, preventing it from taking place. Furthermore, those differences in which this kind of approach has entertained the rules of possibility pushes approaching the most critical space conceivable. For example, we demand to know why the proton mass is only somewhat more significant than the neutron mass. This size difference coincides with the measure of the hypothesis of electroweak interactions. If it were yet insignificantly different, stars would not work. So, we are destined to be pushing against this critical limit. The proton-neutron difference is cramped to what is perceived. If ordinary stars subsist, let us proceed farther. The rules of possibility. These show us what is plausible and what is not. Cosmologists who see a rigid frame that classifies various ranges of values for the necessary constants may claim that related logic might separate Cosmo at the slightest one of these holds galaxies in the standard view. Galaxies produced from minute variations grow more potent by gravitational growth. These are overcome if the cosmological constant is too great. Galaxies will not grow. It is an all-or-nothing prospect. Observers populate universes. The ominous tragedy of no stars, no galaxies. Faced with the influence from the multiverse isolates us at the edge of the multiverse where circumstances are just average. The advantage of the catastrophe approach is that it sets a firm line in superspace, the new ridge. In this view, presented by Lawrence Hall of the University of California at Berkeley, is that the organization of multiverse pressure and catastrophic limits illustrates many of the fine-tunings observed in life. Are we normal, or are we a cosmic fluke? Here is a different way around the Goldilocks dilemma. Maybe we are far from ordinary observers of the cosmos. It has been shown that quantum theory cannot expect us to be everywhere. With high probability, the Copernican principle that the Earth is not the heart of the cosmos returns with a retaliation. Our very survival could be an incredible event. American physicists can determine that it is quite conceivable and not significantly unlikely for us to exist in a cosmos where we are not expected. Cosmological models that foretell that at most limited one example of complicated data exist with possibilities somewhere in spacetime are interchangeable. Despite how many other specific copies exist, this leads to enormous suggestions. Trials in cosmology might become irrelevant because there is no relevant similarity between us and how the cosmos seems. Canadian cosmologist Don Page settles those observations, would score for nothing in differentiating between hypotheses and much of cosmology, would terminate to be an observational science. Now, there is a different understanding of that heartless redneck theory. We would no longer be authorized to use odds, that is, chances to see between Cosmo. What difference would it perform if our cosmos were 1 in 10 to the power of 500? If we could no longer discuss whether this was likely or unlikely, it had to appear somewhere, and it might also be us. This sort of argumentation puts an end to the anthropic principle's naive forms, indicating our unique place in the cosmos. The anthropic observer's role can be examined more intensely as well. Perhaps there are practically no observers. It may be that all, but a few of the 10 to the power of 500 voids that populate the panorama are completely unpopulated by spectators. Physics is unnecessary since quantum theory needs observation. For the truth to be visible in this experiment, Pity Schrödinger's cat was identified for the thought exercise of the German physicist Erwin Schrödinger. The cat is in a case and permanently sentenced to be both alive and dead in a dual virtual reality until the inspection order by opening the box is completed. This heads to one of the most well-known mysteries in quantum theory. The relief of poison gas was triggered in the cat's box by a radioactive disintegration. Intrinsically, probabilistic, the decay transpires, or it may not. But there can be no doubt once the cat's case is open, it is either living or lifeless. Physicists struggle to explain this by assuming that there are two cats, one living, one dead. Only one of these unpredictably actualizes when the case is opened. We get into this predicament because the spectator takes him or her away in the cat state. No longer values the equivalent could be true for nearly all our toxic cosmo. They are barren of spectators and physics articles. The rolling field, which applies the void state into a cosmos, rules so gently that it just appears at its target. Only the longest-lived cosmo get populated. One of these is ours, easily old enough to produce stars. If simply one cosmos made it to this coveted state, we would be given far fewer opportunities to define our continuation. This way, we bypass what has been called the young nest paradox. Why are we so young when unbelievably many more cosmo are far more experienced? Of course, there might be other options such as cosmo with various states of the basic constants. These cosmo would not yet make stars. There would be no other separate universes. Nevertheless, at most limited, there are fewer of them. Our resort here may be to assume that an advanced physics hypothesis will present values of the material constants. We are in a great fellowship, after all, Eddington imagined. So, he measured the precise formation constant to various vital figures from the first principles. Nevertheless, he frustratingly received the wrong answer, defying our biggest challenge, dark energy. Counters cosmologists from relaxing at night. Why is its body so small? When all particle physics theories lead us to a state more monstrous by 120 factors. Usually, there is one argument on the strength of the force of dark energy that merits serious attention. Furthermore, why is it presently working? To dominate the universe's development is hurrying, is driving over physicists. Dislike the concept of fine-tuning, their explanation for choosing what seems an unlikely event. Hence, they have grown up with a proliferation of multiverse considerations. These stink of metaphysics and are irritable to verify science fiction-like progress in time travel technology. They are still challenging to lie with any foreseeable investigations. Nevertheless, it reveals why dark energy needs to be small and analyze its results. When we measure density and homogeneity in the cosmos, we draft them within the temperature variations seen in the microwave background. The level of the variations is negligible. It amounts to 0.001%. If Einstein's cosmological constant, the most simplistic display of dark energy, was greatly more critical than the determined value, galaxies could not have developed from these fluctuations. However, we live in a galaxy, and we would not be hereabouts. Where there are no galaxies, therefore there is an observational prejudice in our considerations. Our residence demands a low value and modern control of dark energy. Of course, one might ask why there should be some dark energy at all, and galaxies are excellent in a cosmos without dark energy. Here the evidence for a cosmological constant, and, hence, for dark energy arises from string theory. String theory is speculation of quantum gravity. It tries to illustrate how the most diminutive and most significant powers in the cosmos, and all significant interactions, were once joined in multidimensional lines before the Big Bang. There are many potential benefits for the strength of the dark energy force. The most likely value is where the number of model choices is most meaningful. This is the most outstanding value. Nevertheless, this influence toward bigness is defined by the requirement for us to observe dark energy and, more particularly, to exist in a galaxy. Therefore, dark energy is necessary minor, and only freshly authoritative Nobel laureate, physicist Steven Weinberg, first read this case for the smallness of dark energy. There are at most minuscule two structural imperfections in this thought. One approaches from statistics. The thoughts always follow the rules of the Reverend Thomas B's namesake of Baz's doctrine. This 18th century statistician stimulated a new form of computing the chances of an incident transpiring, studying all potential theoretical circumstances. The more significant the possibilities, the more apparent it is to promote one of these selections. So, we required a total witnesses. It sets out that if one concedes for the actual number of observers and the future no in any given cosmos, the chances shift dramatically. Infinity forever wins. When employed, Boss system promises that near zero dark energy cosmo are valued. There are far more universes per unit volume connecting all the cosmo with zero and minimum dark energy than those with high dark energy. So, the higher fixed on dark energy persists, but there is no longer any predictability. There should never be dark energy. Our efforts to determine anticipated amounts of dark energy only worsen even. The higher tide on dark energy is not a sturdy discussion. Here is why, if variations could be significant, originally, this would reduce the force on dark energy. The general study says that enormous black holes sooner than galaxies would set quite shortly in the universe. However, this analysis implies that the primordial fluctuations are generated by enlargement using the enlargement field. This is an energy field with no favored way. We describe such an energy field as a scalar field, rather than vector fields of energy. Directed, this field provides the energy that produces extension and causes the quantum variation that seeded galaxies and are perceived in the microwave sky. The varieties are like advancements in matter and radiation. If two giant black holes would generate and eventually govern the cosmos, this is not for crisis. Any argumentation about expansion has loopholes. One is that there is no single energy field that drives expansion. String theory determines that there would be a comprehensive slew of scale of fields. The conclusion is that the most basic primordial settings consist of two different varieties. One follows to the concentration of material and radiation. This amounts to a small rise in the local curving of space. Einstein shows us that this excess gravity ultimately causes galaxies to deflate once the cosmos is cooled down and is controlled by conventional matter. These are the variations expected if a single scalar range stimulates expansion. There is now a different type of variation in which an under-density counterbalance for an over-density material and radiation. They require no longer be a simple curvature inconsistency at all. There are even variations with zero deflection. The tidal clavidin has been assigned to the organization of fields that can produce zero curvature variations. Moreover, because the radiation frequency is so tremendous early on, one can compare this with an enormous material fluctuation. Great inconstancies in the material are reasonable, but because of the scales with radiation pressure, any chance of early black hole production is bypassed. On the orders of galaxies, the variations could be more meaningful by some 20 factors than the natural curving fluctuations and still head to pleasant microwave background temperature ripples. Galaxies would form fresh as shortly as the cosmos consisted of thermonuclear hydrogen and the radiation finished strewing, facing the electrons. This lasted 1,000,000 years following the Big Bang, but the galaxy mass fails would develop and form stars. The resulting cosmos would not be a reproduction of what we perceive. Nevertheless, this barely matters. The arched cosmos would include an abundance of galaxies, stars, and planets. It could hold a far more substantial dark energy content than our perceived universe. It would unavoidably carry observers. We cannot apply galaxy formation to produce any significant pressure on dark energy. Mathematics may have the ultimate say in picking our cosmos. Possibly specific rules of mathematics that work in the most profound regions of existence have directed that we have the cosmos. We hold such proof would create an impregnable event. The conventional form of particle physics is a crucial component of string theory, which, as seen earlier, is a hypothesis of quantum gravity one-dimensional waves paint particles. In a greater dimensional field, strings subsist in a 10-dimensional hyperspace. This presents a mathematical description of all of particle physics. Particle masses are essential to the hypothesis. As is supersymmetry, the hypothesis is still unfinished, but it performs the most compelling story of the universe's beginning. Supplied with string theory, one obtains a certain number of potential geometric spaces, either one of which could ultimately compact Alpha into our cosmos. If we use supersymmetry as our guiding system, there are 10 to the power of 500 of these places called Carleville manifolds. Each is a forerunner position of a potential cosmos. Each concedes 3 generations of particles. Therefore, all associated particle physics can be included in every one of these manifolds. The cost one gives is that all hold 6 dimensions. These subsisted at the Planck moment at the universe's origin. When gravity was associated with the opposite significant forces, this was the tale of quantum gravity. Our universe has 4 dimensions -3 in space and 1 in time. As the cosmos unfolded away from the planet density and chilled, the gravitational communication became much smaller than the nuclear forces. At the same time, the additional dimensions contract challenged. One of the manifolds that became our cosmos, there may, however, be evidence on microscopic layers of protected dimensions. These would show themselves as tiny variations from Newton's rules of gravity. On microscopic scales, physicists are hunting for such conclusions, but have not encountered any. There may also be evidence of hidden dimensions on gigantic measures. Not all thought of the Big Bang universe local bin, deleted by the condensed application. Again, no notable differences from Einstein-Newton's gravity have so extensively been seen. How do we organize the excess of early cosmos? The scientific hypothesis is that there need be a sort of topological similarity to a viable form. You have been listening to Mysteries of the Cosmos, challenging enigmas that astrophysics are trying to solve.